power and better energy. That's why it's in the diagonal direction. Okay, so what are the options? What are the options? Again, you coming back to the two techniques that we all know of, battery and the supercapacitor, isn't it? So here we already discussed that supercapacitor will have huge power density. On the other hand, battery will have huge energy density. That's the trade-off, right? So in one of the approaches, what people have recently looked at is something called a hybrid nature. Okay, that's a new addition to the capacitor, right? Instead of two similar capacitive electrodes taken in a supercapacitor device, can we instead take a hybrid approach? What do I mean by a hybrid approach? In a device very similar electrochemical device, can I replace one of these electrodes by a battery type electrode where typical redox reaction happens? The other electrode is typically a porous carbon based electrode where the normal EDLC, like the electric double layer capacitive reaction happens, right? So you form a device out of this, right? What is the advantage here by forming this kind of device? Then what happens is, like, two different mechanisms operate here, right? On the right hand side, the capacitive electrode will have a typical capacity charge story, which means like the ions will absorb onto the force, power is good. Whereas onto the left hand side, which is a typically battery electrode, it will have these ions getting actively involved in a redox reaction, oxidation and reduction happen, which means like there could be an intercalation of these ions into the material. Charge storage capacity will be high, energy is high, but power is low. So one guy will take care of the energy aspect, the other guy will take care of the power aspect, isn't it? Right? It is something like the good old story of our bedtime story about this, tortoise and this, rabbits and tortoise, isn't it? Rabbit is very good in power because it can run 100-meter dash, but 100 meters it is collapsed. Whereas tortoise instead, it has huge energy density. Power is bit low. We cannot do a 100-meter dash and all. It will go marathon. It will go very slowly, but it will cover larger distance. Energy is high, right? So one day these two guys decided that there is no point in we individually racing like this, right? Why don't we work together, right? So tortoise said, rabbit, why don't you just climb on top of me, right? Then we will win the race. Similarly, in this kind of hybrid technologies also, we are using that similar analog, right? Both energy and power is brought in while appropriately choosing a battery electrode combined with a capacitive electrode. Okay, it's a relatively new concept, right? 2 years back started, and this is what typically see here, right? Onto the capacitive side, you can have carbon. It can be a graphene like material put at the carbon where the charge is stored, like anion CF6 minus gets stored here. On the other hand, right, typically this is an intercalation. That's why you get a plateau here. There is no plateau on top because it's purely capacitive. Whereas at the bottom, the anode, it is typically a redox reaction. That's why you get a plateau or a peak in the cyclovoltamogram, right? It forms a capacitor. And the difference between these two voltages, you get the voltage for the capacitor device. Okay, I hope that is very clear, right? Something like this, right? I use a porous carbon as a cathode, and there is something called, any oxide material will do, like a lithium titanate, lithium titanium oxide, right? So the mechanism is like this. The lithium ions, the cation, will just get intercalated at this point when I'm charging the battery, when I'm charging this device. At the same time, while lithium ions get intercalated here, the anions, like the CF6 anions, will get absorbed onto the porous carbon, right? These two processes happen simultaneously when I'm charging. And once it is fully charged, this side is fully occupied with lithium ions, this side is fully occupied with the CF6 minus. Then when it discharges, which means like when I use it for some useful application like powering the lamp or something, these two ions will, get back to the electrolyte. Okay, it gets back to the electrolyte. And that's the mechanism typically we talk about it, right? And we have, we're quoting examples, we have done several work in this area, something called, now I'm replacing lithium because lithium is expensive, lithium is abundant in nature, so we wanted to go for a much more abundant and cheaper material, cheaper chemistry, and that's why there is a lot of interest for sodium.